Well, hello and good evening. I'm delighted to welcome you to this Centenary Inaugural Lecture. For those of you that don't know me, I'm Professor Sarah Davis, Head of the College of Science and Engineering here at the university. These events are such an important celebration of academic achievement and the promotion to a personal chair. These occasions bring together colleagues past and present from the university and beyond, and very importantly, are shared by friends and family. So welcome to you all. This academic year, we're celebrating the university's centenary, and physics at Leicester is slightly younger than the university itself and was established in 1924 alongside chemistry after an appeal to raise £20,000, something like the equivalent of 1.3 million today, to fund the development of laboratories. So today, physicists from the University of Leicester are engaged in a wide variety of world-leading projects, from the exploration of distant galaxies to improving our understanding of our home planet. And at the forefront of space research, this is one of the largest space research-focused universities in the UK and Europe. We've contributed to international space missions for 6 decades, with at least one Leicester-built instrument operating in space every year since 1967. And so with that proud heritage and an exciting future ahead of us, we're really privileged to hear from one of our leading scientists in the School of Physics and Astronomy. But before we do, I'm going to hand over to Professor Emma Bunce as Head of School to introduce this evening's speaker. Over to you, Emma.
Thank you, Sarah. Good evening. My name's Professor Emma Bunce and I'm the Head of the School of Physics and Astronomy. I'm delighted to be able to introduce Professor Mark Wilkinson today on the occasion of his professorial inaugural lecture, having been promoted in 2019. These are such important occasions for us, as the appointment to professor is a great honour for an academic. And importantly, these lectures offer a fantastic opportunity to showcase the world-class research being undertaken here in Leicester. Mark began his academic career at Trinity College, Dublin, studying theoretical physics at undergraduate and master's level. Mark's subsequent PhD research in theoretical astrophysics was undertaken at the University of Oxford with Professor Wynne Evans, during which time he studied the Milky Way and Andromeda galaxies. His thesis work provided a significant result in the form of a new mass estimate of the dark halo of our own galaxy, work which is of continuing relevance today. Mark continued his research beyond his PhD with the Stellar Populations Group at the University of Cambridge, where he investigated the properties of dwarf spheroidal galaxies orbiting the Milky Way, objects which provide an important window on the study of dark matter. Mark joined the University of Leicester in 2006 when he was awarded a highly prestigious Royal Society University Research Fellowship in recognition of his research excellence. This fellowship supported Mark's work for the next 8 years and led to influential and highly cited papers on the dark matter distribution in these galaxies. During this time, Mark combined his theoretical expertise with programmes of observations to answer key questions relating to our understanding of dark matter. Mark incorporated the use of numerical simulations, statistical methods and dynamical modelling into his research with a view to extracting the maximum scientific value from large-scale observational datasets. Since July 2017, Mark has been the director of the STFC Dirac High Performance Computing Facility, the main national provider of HPC services for the STFC theory communities in astrophysics, particle physics, cosmology and nuclear physics, and hence the overall delivery of the STFC theory research programme. Through this substantial role, Mark provides the strategic plan for Dirac and secures funding for the infrastructure required to deliver the Dirac science programme. Mark is a highly valued colleague and a key member of the physics and astronomy community here at the University of Leicester, and it gives me great pleasure to introduce Professor Mark Wilkinson to give his lecture entitled How to Train Your Telescope, Hunting for Dark Matter with High Performance Computers. Over to you, Mark.
Thank you, Emma, for the very kind introduction, and thank you also, Sarah, for your introduction. Welcome everyone to my inaugural lecture. Thank you all for coming this evening. I know you haven't probably had to travel very far. I'm sorry it's not in person, but in fact, the fact that it is a virtual lecture actually means there are some people, I think, in the audience who wouldn't otherwise have been able to attend. So it does have a bit of a silver lining. So over the next 3 hours, don't worry, that's a joke. I know jokes don't work very well when I can't see you and I can't hear you, but I hope you're all chuckling at this point. So over the next 50 minutes or so, I will introduce you to the universe of dark matter. And I'll talk you through how we've been using high-performance computers or supercomputers to understand the nature of dark matter and tell you a bit about where we're looking in the future. And so with that, I will start my presentation. So the title of the presentation, as Emma said, is How to Train Your Telescope. And the title slide I'll just talk you through now. On the right-hand side, you have the obvious reference to the DreamWorks film contained in the title itself. And two examples of telescopes, so the James Webb Space Telescope and the Square Kilometre Array radio telescope, which are going to be used for hunting dark matter and many other things in the very near future. And on the left-hand side, I've got an image of the William Herschel telescope on La Palma, where I've spent many nights during the early 2000s observing stars in other galaxies. Even though I'm a theorist, as Emma said, I do have experience with telescopes, so the image there is just to show that I have actually sat at the control panel of a telescope. Though those of you who know the William Herschel telescope, the astronomers in the audience will know that actually that's not the control panel that the scientists use. That was just posing for a photograph. And above it, here we have an image of the latest supercomputer that we've installed as part of Dirac at Leicester. And I'll explain in the course of the talk why this combination of telescopes, observations, and computers is so important. So the outline of the talk is I'll give you a brief introduction to dark matter. I'll talk through models of dwarf galaxies, dwarf spheroidal galaxies, which I've spent a lot of time working on over the last 20 years. I'll then describe the Dirac high performance computing facility that I've been director of since 2017. And at the end, I'll talk about the future, both in terms of where high performance computing in the UK will be going, and also more generally how artificial intelligence and machine learning are becoming increasingly important for building theoretical models. So the How to Train Your Telescope is the title of the talk, and because this is a physics lecture, I wanted to make sure that we've got our definitions clear about all the words in that title. So first of all, train. Well, training a telescope, you'll all be familiar with the idea of directing, pointing, or aiming the telescope. Training is also used in the context of teaching a person the skills for a particular job or activity. And more recently, training is the word used when you provide an artificial intelligence algorithm with data that it can learn from. And in the course of this talk, I'll be using train in all of those contexts and explaining how they're interconnected. Telescope, you may think you know what that means, but just to be clear, it's an optical instrument used to view distant objects. Or rather, that was the original definition of the word telescope. Now, of course, it's an instrument of analogous design, which is used to study distant sources, and that can be of radiation, any radiation, often lying outside the visible spectrum. So not just optical. And so on the right, you've got an image of the Square Kilometre Array, the radio telescope I mentioned earlier. And the third use of the word telescope that I'll use in this presentation is a supercomputer. And you might call that a telescope for theorists. And part of the goal of this of my lecture is to help you see why that analogy is actually a valid one, that supercomputers really are the telescopes for theory. So this slide shows a summary of the history of the universe in just one slide, going from the Big Bang here at the dawn of time up to the present day, about 14 billion years later. And what we would like to do in astrophysics and cosmology is understand how this evolution happens. So how do you get from the hot, dense universe as it was very shortly after the Big Bang in a tiny fraction of a second to the myriad of stars and galaxies that we see in the universe today. And in order to understand that evolution, we need to do calculations and observations of things that are happening on many different physical scales, from the scale of individual atoms up to the scale of the whole universe. So what we're trying to do is to see, can we get from this image, which which shows you the distribution, it's the cosmic microwave background from the Planck satellite, and it shows how the density of the universe varied shortly after the Big Bang, about 380,000 years after the Big Bang. So the differences in color show differences in density. So some bits are, it's not smooth, some bits are more dense than others. So that's essentially what the universe looked like after 380,000 years, and we want to understand how did it get from looking like this to looking like this, this is an image of the Andromeda Galaxy. And how do we do that? The tools that we have at our disposal are observations, of course. They are like experiments in the sense that we only have one universe, so we're not at liberty to just produce another universe and see how it's different in the way you can in a normal physics experiment. So observations are the best we can do. We can look in different directions and we can look back in time because we can see things as they were in the past. We also need physical models. We actually need to have an understanding of what it is we think we're looking at and use our understanding of physics to explain that. And that allows us to interpret the data that we see. And now, in the last decades, computer simulations have become increasingly important, and we use high-performance computing, or an equivalent word, supercomputers, to do these calculations. So in my research, I've been using a mixture of these three in order to develop our understanding of dark matter. But the same is true of many, many fields now. So if you want to form a galaxy, what are the key ingredients that are needed? Well, first of all, there's dark matter. I'll talk more about that shortly. Then there's gas, which we know has to be there because we know that there are stars, and stars are formed of gas. You need gravity, that holds everything together. You need to understand gas physics because something turns the gas into stars, and that's where star formation comes in. We know from a lot of observations there are black holes, and these play a key role in galaxy formation. I won't have much time to talk about that today. Something called feedback, which again is the interaction between the black holes and the gas in the galaxy. The ... represents the things we probably don't know at this stage. And then somewhere in between, somewhere after that, you get to planets and life and other things. So these are all the ingredients. So now the thing I've been focusing on in my research is the dark matter component and how that, what that is and how it affects the other aspects. So this slide shows the components of the universe, how it's made up, how the mass of the universe is made up according to our current models. So about 4.9% of it is ordinary matter, which is basically everything that you're familiar with. All the visible matter in the universe falls into that category. 26.6% is dark matter, which I'll talk about and tell you what we know shortly. And 68.5% is dark energy, which I'm not going to talk about in this talk. That will be a whole series of lectures in its own right. But as you can see, it's a major component. And just as an aside, when I started my PhD thesis in 1996, dark energy was not part of this pie chart, and there are actually only two things. 5% was ordinary matter and 95% was dark matter. By the time I'd finished my thesis, so in 2000, 2001, the observations had actually changed. The data had shown us that our understanding wasn't right, and so dark matter had been reduced to only a quarter of it. But the key point to note here is what we see in the universe is only a tiny fraction of all the mass that's out there. the vast majority is this dark matter and dark energy, neither of which are directly visible. So why do we think there is dark matter, and what is it? So if you go outside on a dark night, you'll sometimes see the Milky Way if you're lucky enough to be far enough away from city light pollution. And it looks something like this. This image is actually, I show this in presentations because it's actually, it looks like a photograph, but it's actually a hand-painted picture of the Milky Way, which was produced in the Lund Observatory in 1955. If you're ever in Lund in Sweden, it's really well worth looking at it. It's a very, very impressive image. And the stars were painted on individually, and the gas was spray painted on. So this, the bright parts here, sorry, not the gas, the individual stars are shown as points, but then the kind of regions where there's higher densities of stars were done with spray paint. When the image was first shown, people looked at it and said it didn't look realistic because the stars were too sharp. So they had to go around each individual star and spray paint a little bit more to make them look suitably blurred. But it's a really impressive image. And so this, of course, is only the visible matter. This is only things that we can observe. That's what the Milky Way looks like from inside. That's what it looks like if you look up at the night sky. From outside, this is what we think it would look like. So we think it's a disk galaxy. So it's got this large extended flat disk, and then in the center it has a what's called a bulge. And for those of you who are not astronomers and are unimpressed by our originality of nomenclature, I'm sorry, but we just describe things exactly as we see them, hence disk and bulge. This image again of another external galaxy looks what we think the Milky Way would look like if you looked at it from the top down. This is to give you a sense of where we are in the Milky Way, and we're about 2/3 of the way out. It's a disk galaxy with spiral arms, and we're about 2/3 of the way out from the center. And again, just to emphasize, what you're looking at here is material that we can see, stars, gas, and dust in this case. So where did this idea of dark matter come from? Well, the first signs of dark matter were detected in 1934 when Fritz Zwicky, shown here on the left, realized that the galaxies in the Coma cluster, which is shown here on the right, were actually moving too quickly. So just to give you a sense of what you're looking at here, the objects with the crosses on them are stars. Everything else is a galaxy. All these little dots are all galaxies. And so those galaxies form a large cluster of galaxies, and they're all moving around each other. And what Zwicky realized was the galaxies were moving too quickly, and they shouldn't have stayed together for so long. They clearly had stayed together because the galaxies were very old. So something was holding it together, and he called that unseen matter or dark matter. Now, as you might infer from the picture on the left, Zwicky was a rather difficult person to work with. And so it wasn't until much later when two other people, Vera Rubin, who died recently, and Albert Bosma, did a lot of work on the nearby galaxy M31 and showed that actually it wasn't just in big galaxy clusters that you found dark matter or a need for dark matter, but also in ordinary, what we call ordinary galaxies like our own. And what they realized was that the stars and gas in the Milky Way and its neighbor Andromeda are actually going round much too quickly. And what that's shown in this graph here. So you have a graph here of position in the galaxy and the speed or velocity that the gas and stars are rotating. Now, if the only thing that was holding the galaxy together was the gravity from the material that you could see, you should only be able to go at the speed shown by the blue curve. So out near where we are, that would limit how fast things could be moving. But in fact, out near where the sun is, we're moving according to the orange curve. So we're moving at about 220 kilometers per second. And again, the Milky Way should not have stayed together. It should have just flown apart unless there's something else holding it together. And if you do the calculation, you need about 10 times more dark matter than visible matter in order to hold the galaxy together. Now, I commented earlier that I implied it was the only reason why the community accepted dark matter after these rotation curves became available was because Vera Rubin and Albert Bosma smile more and were easier to work with. So one aspect of it is that the data had improved, and there was a lot of work done on other galaxies as well. The other thing is, I spoke to Albert Bosma. He actually saw a version of this slide several years ago, and he pointed out he actually knew Fritz Zwicky, and he said that he always got annoyed when he saw people showing the photograph I showed you earlier, this one, because that was very unrepresentative. He was actually pulling a face. That's an outtake from another much larger photo. And this is a much more representative picture of him. So I just thought I would correct the record there. So I've said that there's evidence for dark matter in disk galaxies coming from how fast things are moving. And just to put that into a mathematical formula, it's shown at the bottom here that you can calculate the VC squared, which is the square of the velocity the gas is moving, or the stars, and that's on the left, and that is equal to G and R, so R is the position, times M, where that's the mass. So you can use that formula to tell you for a given speed that the gas is moving, you can work out how much mass has to be there in order to hold the gas in its orbit. Now, that's one way to measure the mass of a galaxy, but actually if you look in this image of the Andromeda Galaxy, there's several other objects. There's this galaxy here and this galaxy here, and so there are several other smaller galaxies which are traveling around the Andromeda Galaxy. And in fact, you can measure how fast they're moving, and likewise there are galaxies like that going around the Milky Way. You can measure how fast those galaxies are moving and use how they're moving to tell you how heavy the Milky Way has to be, how much mass there needs to be in the Milky Way in order to keep them in orbit around the Milky Way. So if the Milky Way is too light, those galaxies would just fly away. And so Emma mentioned this result in her introduction. So during my PhD thesis, I worked with my supervisor, Wyn Evans, on looking at what the mass of the Milky Way halo is, so the dark matter that surrounds the Milky Way, how much mass is in there. So the details of the models are on the right-hand side, but what actually I want to focus on is the plot. Now, this for the astronomers in the audience, they'll be more used to looking at plots like this, so I'll just talk you through it in a bit more detail for anyone who's not used to it. So what you can see here is on the x-axis, you have a parameter called beta, and basically that's a parameter which tells you whether the stars are moving and whether the objects are moving in circles or moving, well, that's -1, or they're moving in straight lines, and that's 1. And on the y-axis, you have the mass that is implied in that case. And what you see is the contours are basically showing the regions where you can get a good fit. And so if I can find my cursor, the contour that's surrounding the plus sign is the contour that you should focus on. And that's basically telling you that in there's a reasonably good chance that that's the mass of the Milky Way, and the numbers at the bottom tell you those. Now, the thing I wanted to highlight is this is a logarithmic scale. So the error bars on this calculation are huge. They're dominated by the fact that it's very hard to measure how fast all the things are moving around, but they are enormous. So if you look at the error bar in the mass, it's a factor of several. Now that was actually a very good result at the time, and it was much more precise than previous ones. And actually the most significant bit is in the dotted contour. The dotted contours are similar to the solid ones. And again, the reason for the difference between them is there was one data point which no one was really sure whether it should be included or not. And previously, all estimates depended on whether or not you included it. And the modelling that we did showed you could actually build a model where it was much less sensitive to whether you did or didn't include that. So the main result to take away from that is that we had an estimate of the mass of the Milky Way halo, and it was relatively independent of what you assumed in terms of the objects that were bound to the galaxy. So I've said that we need dark matter in galaxies, and so what does the dark matter actually do in terms of the evolution of the universe? So this is a computer simulation done by colleagues in Durham at the Institute for Computational Cosmology, and it's called the Eagle simulation. And what it's doing is looking at the formation of a galaxy like the Milky Way, and looking at it from early in the universe until the present day. And so the Virgo Consortium are the group that did the research, and it was done on one of the Dirac computers. And in this particular image, you're just looking at the evolution of dark matter. So this is only dark matter. There's no gas and stars. So the colors are telling you about the speeds at which things are moving. So yellow things are moving faster than red things. And also the brightness is telling you how dense things are. So what you can see in this, as the simulation progressed, you started out with things relatively smoothly distributed, and then everything clumps together because of gravity. And the clumps merge together so that small clumps merge together to form bigger clumps. And in this later, as we're now zooming out a bit, you'll see bigger clumps are now merging together to form other galaxies. So the two things to take away from it are gravity dominates the evolution of this of the universe and on this scale, and it is the dark matter that makes things collapse in order to the gravity from the dark matter is what's controlling where the galaxies will form. The other thing to notice is that around each galaxy like this one, there are lots of smaller galaxies. And so, or in this case, I should say these are dark matter halos. You've got a big dark matter halo here with a lot of smaller dark matter halos around it. And so you might be tempted to say, well, in the picture I showed earlier, where we have a large galaxy and we have smaller galaxies around it, maybe they're the same thing. So maybe the galaxies that we see around the Milky Way correspond to the galaxies that are in, or the halos that are in the simulations. But we don't know. So that's a lot of my research has been trying to work out what's the correspondence. Do the galaxies that we see around the Milky Way correspond to the objects that we see in simulations? So the image that's here is of the Andromeda Galaxy, and it shows a couple of the satellites of Andromeda here and down here. They're called dwarf spheroidal satellites because they are small, hence dwarf, and spheroidal because they are round-ish. And in fact, from within the Milky Way, so these, from a distance, these look quite well defined, and it's kind of obvious that there's something there. When you look from the Milky Way, these are two of the dwarf spheroidals that orbit the Milky Way. The one on the left is the brightest one, so you can see there's a definite concentration of stars here. The one on the right is one of the faintest ones, and actually in this image there's only a handful of stars that are visible that are part of it, but I can assure you there is a small galaxy there and a lot of dark matter. And so the question is, do these galaxies, do these objects that are going around our galaxy, do they have dark matter in them? If they do, then maybe they're the objects that we see in the simulations. So this is a plot from Matt Walker's work looking at what's called the dispersion profiles. Now, earlier we were looking at rotation curves, so how gas moves in a disk galaxy. In a spheroidal galaxy, so a galaxy that's not flat, the stars are moving in all directions. So instead of measuring, they're not just going in circles. So instead we need some other number that shows whether they're moving quickly or slowly. So that's called the velocity dispersion. So the bigger the velocity dispersion, the faster stars are typically orbiting within the object. And what you see from this, the data points are from a huge survey, many observations that Matt Walker did systematically in the course of his thesis at the University of Michigan and subsequently. And what's important is, in all cases, the dispersion profiles are large, the numbers are large, so they're all between 5 and 10 kilometers per second. So that already tells you there's quite a lot of dark matter, because again, if that without dark matter, they would just all disperse. But also they're flat at large radii, so it doesn't, because the stars at the edge are not moving more slowly. And just like in the Milky Way, where we saw the stars at the edge were moving quickly, and that told you there was dark matter, the same is true in the dwarfs. The stars are moving quickly, and that tells you there's a dark matter halo in these galaxies. And so in 2001, so prior, with a much smaller data set than the one I've just shown you, Jan Kleine and I, working with Wyn Evans and Jerry Gilmore, showed that from a data set of, it was about 160 individual stars, we were able to show that there had to be an extended dark matter halo in Draco. Not just that there was some dark matter, but that the dark matter extended beyond where the stars were. And so the key plot for that is this upper panel here, which is basically showing the probability of various different models. And so over here you've got mass follows light, so that's essentially saying the dark matter is exactly mirrored by what you see. So that would mean that the dark matter was not more extended. Over here, the dark matter is very extended. And in the middle, the dark matter is similarly extended to what you see in something like the Milky Way, relative to the size of the galaxy. And so what the probability is telling us is, we can definitely, we can't really tell whether exactly what shape the halo is, how extended it is, but we can definitely tell the halo extends beyond the edge of the light. And so it was an important result, because that implied that there was a good chance that these dwarf spheroidal galaxies were some of the objects that were seen in simulations. The complication is that dwarf galaxies are actually have contributed to building up the Milky Way. And the problem is, the ones I showed in the image earlier around Andromeda, those ones are galaxies where they are they're quite obviously there, in the sense that they're moving around and they're still all hanging together. But if you're a dwarf galaxy and you're going around a big galaxy like the Milky Way, what tends to happen is you get torn apart. So just the way that the moon orbiting the Earth exerts tidal forces that cause the tides on the oceans, as a small galaxy goes around the Milky Way, essentially it gets stretched out by the gravity of the Milky Way. And what that results in is things like this. So this is an image by Vasily Balakarov, which shows the stars in the halo of the Milky Way. So this is stars outside of the disk. And what you can see is it's clearly not a smooth distribution. And there are some very obvious features like this, and this line here, and this one here. And what's interesting is this line of stars here has a bright dot in the middle, and that actually turns out to be a star cluster that has tails of stars being ripped off it by the Milky Way. The larger, fatter ones actually correspond to the remains of a galaxy, or the tails coming off a dwarf galaxy called Sagittarius. And this one here is called the Orphan stream because the progenitor couldn't be detected at the time. There's various theories now as to what the progenitor was. But this shows that dwarf galaxies have certainly, there have been dwarf galaxies disrupted, but it also then calls into question the models that we're using of dwarf galaxies and treating them as if they're nice little spheroidal objects on their just sitting there with the stars moving around inside them may not be a good model if they're constantly being buffeted by the Milky Way. So this is an example of how that map can be generated by the Sagittarius galaxy. But I think more useful is perhaps this image, this movie. So here you're looking at a galaxy orbiting in the Milky Way, and this we've masked out the stars and gas of the Milky Way so that you can see the galaxy, because it's a dwarf, and so it would be too faint otherwise. And so it's orbiting around the Milky Way, getting stretched and torn apart. And what that means is at certain times in its orbit, such as where we stop the simulation, there is still a well-defined blob of stars, but there's a lot of debris behind and in front of it. So if we were sitting here looking at this galaxy, we'd see stars that were still contained within the galaxy, but also some of this debris. And so one of the things we looked at, this was work done by my student Ural, we looked at what we call disequilibrium modelling, so trying to measure the mass of the Carina dwarf, taking into account the fact that it was falling apart or being disturbed by the Milky Way. And so the question was, if you had a galaxy like this, would it look anything like the Carina dwarf, which is a particular one we had data for? And the plots on the right show that the answer is yes. So here we have the data points or observations of the surface brightness. That's basically the number of stars per unit area. And so that's basically telling you that in the center, the stars are more concentrated and brighter, the galaxy is brighter in the center than at the edge. And you can see that our models do a good job there of representing them. And here you have the velocity dispersion profile that I mentioned earlier. So that's telling you how fast the stars are moving. And again, our models, the data are not great. We needed more data at the time, but you can see that the theoretical models, which come from the simulations, are doing a reasonably good job of reproducing the data. The key important thing is here. So this delta V in both of them, in the green and blue, it's two different simulations, and it's essentially measuring when you're looking from this point up at the dwarf galaxy, because the stuff that you're looking at on one side of the galaxy is in this tail of debris, and on the other side it's in this tail of debris, there's actually a big difference in velocity between them. And so if you measure the mean velocity across the face of the galaxy, then you can try to detect evidence of these tails. And so what we found was the observed data were telling us, giving a velocity gradient of 7 kilometers a second. So that's a difference between here and here of 7 kilometers per second. And our models were doing a reasonable job of reproducing that. And the really cool thing with this is we could then say, well, if a galaxy like Carina fell into the Milky Way, how heavy could it have been when it started falling in and still show some signs of disruption? Now, what do I mean by that? If a really massive galaxy falls in, Milky Way can't really do very much to it, very much damage at all, and it can go around for a long time without being harmed. Whereas if a small galaxy like the Milky Way, like Carina, falls in, then it will get damaged. And because Carina is not badly damaged, it's just got this hint of having been affected by the Milky Way, we could set an upper limit to how massive it was. And so this was a paper we had in Nature Communications in 2015, showing for the first time what the likely mass of the Carina dwarf was when it fell into the Milky Way. And so it showed, what you see here is the data points from our simulations, or the red and black data points, and they are systematically, so you've got the mass of Carina when it fell in along the bottom, and on the y-axis you've got the stellar mass of Carina. And what you see is our data points are giving a relatively low mass when you compare them to lots of simulations, which is all the data points on the right-hand side are from various different simulations that have tried to reproduce the data on dwarf galaxies. And so what that was suggesting was actually Carina was kind of surprising, a bit of an outlier in terms of where the theoretical models were predicting. So we've now seen that there's dark matter in the Milky Way. We've talked about how that's measured. I've talked about how there's dark matter in the dwarf galaxies around the Milky Way. I'll just briefly talk about a few things that you can learn about dark matter from studying the dark matter in dwarf galaxies themselves. So one thing you can do is, we haven't talked about the question yet about what is dark matter. So one thing you can use the dwarf galaxies to do is give you some clues to that. Now here are the output of 3 simulations with different types of dark matter called warm, hot or cold. So the details of the models don't matter. What matters is if you look at the bottom, which is what a galaxy halo looks like at the end of these simulations, there's an obvious difference that cold dark matter models on the bottom right-hand side have lots of little objects around them, whereas hot dark matter, the one on the left, don't. So if you can be sure that the dwarf galaxies you're looking at correspond to these things we're seeing in the simulations, then in a sense you could just count them and say, well, we've got more dwarf galaxies than you would expect in a hot dark matter model. So that shows that dwarf galaxies, because they seem to correspond to dark matter halos and simulations, are objects that are very interesting for telling you about the nature of dark matter. I'll just point out in passing that dark matter, the way I presented it to you is from the astronomy and cosmology perspective, whereas basically we were having trouble understanding how the stars were moving in galaxies. So we said, well, the galaxy must have this unseen component that's really heavy, and everything is okay with our models if you put in this invisible bit. And so if any of you are uncomfortable with that and thinking, well, are they just making all of this up? I'll just note that in particle physics, dark matter is nothing unusual. So there are many, many types of particle that are being studied at, for example, the Large Hadron Collider in CERN, which could be dark matter. Now, it turns out many of them are being ruled out, so we're not out of the woods yet, but it's certainly the case that from a particle physics perspective, dark matter is just another type of particle. It's just a particle that happens to not emit light. But because of that, dark matter can be detected in other ways than I've talked about detecting it indirectly up to this point, but actually you can potentially do a more direct detection, because dark matter, if it really is small subatomic particles, there's a possibility that those particles can bump into each other, annihilate and produce gamma rays. And it might be possible to detect those gamma rays. So in this plot, which was from a paper with Bonivar et al. In 2015, we looked at how the signal from dark matter, the gamma ray signal that you'd see from upcoming upcoming gamma ray telescopes, how that would compare to other things, and the most important other thing being the background of gamma rays that are produced by other things in the Milky Way. And the key thing to take away, the 2 key points to take away from this plot are, first of all, quite a few of the dwarf galaxies, most of the ones, in fact, so all the data points in the plot are showing you what our predictions were for the observations, and they're all above the background that's predicted for the Milky Way. So that means, in principle, if the dark matter, if the dwarf galaxies contain dark matter, and if the dark matter is in a halo that's centrally concentrated around those galaxies, then there would be a possibility to detect it using gamma rays. And so this is, up until this point, everything I've been talking about has actually been in the optical or near infrared. And so there we were training our optical telescope. This is an example of training a gamma ray telescope, because essentially here we're saying, if you want to find gamma rays, if you want to find the gamma ray signals coming from dwarf spheroidal galaxies, this basically gives you a target list. So you can pick the one that you think is going to give you the largest signal. I've added in this slide as an extra. This really is an aside, but I thought I'd put it in because there was a recent paper earlier this month which it relates to. So I'm just throwing it in really as a hostage to fortune in case this turns out to be correct. So there's a question, could dark matter be made of black holes? And so with a summer student, Shoko Jin and Jerry Ostreicher in 2005, we did some simulations, or Shoko did some simulations to look at this question and see, could you make a galaxy that looked like a dwarf galaxy if the dark matter was made of black holes? Now, the main challenge is, if the dark matter is made of black holes, then actually black holes are heavy objects, they're all flying around, and they would actually bump into or come close to the stars in the galaxy, and you'd have this serious risk that the black holes would essentially kick out all the stars, and you'd end up with just a blob of black holes only. But what we showed was, and this is what you see in the plot on the right, which is again the dispersions, that's telling you how fast the stars are moving. The circular bits, the data points with circles on them are the solid dots are the observations for that was for Draco, for one of the particular Milky Way dwarfs. The open circles are for the simulation as it started, and the squares are how the stars, as you can see, are moving faster later at the end of the simulation, because they've been buffeted by the black holes. And so what this is essentially saying is, if the black holes have masses about 10 to the power of 5 times the mass of the sun, so 100,000 times the mass of the sun, not too much smaller and not too much larger, then you probably could just about make the halos of dwarf spheroidal galaxies out of black holes. And the paper that came out by Capaluti et al. A couple of weeks ago was essentially saying that reviving this idea and saying that the James Webb Space Telescope may actually be able to provide more information on this question. So everything I've talked about so far has been about the dark matter in dwarfs, but I did just briefly mention there that the stars are there as well. So another question that's of interest is, how do you actually form, once you've got one of these little dark matter halos, how do you actually form a galaxy inside it? So with a student, Claire Cashmore, in a few years back, we did some simulations, and here what you're looking at is the gas in a dwarf galaxy. And the reason there's these bubbles appearing every so often is that the gas is being blown by stars exploding. So stars are forming, some of them turn into supernovae, and the explosion blows away some of the gas. And what's interesting here is on the left-hand side, you've the dwarf galaxy starts out as a spheroid. So it's basically, it starts out looking a bit like the galaxies we see now. Sorry, I have that the wrong way around. I'll correct that, and maybe in the edit it can be changed. The one on the left is where the stars are in a disk to begin with. The one on the right is if the stars, if the gas was initially in a spheroid, so looking a bit like it is today. And there's an obvious difference. By the end of the simulation, the one on the object on the left is still there. It still has stars and gas. On the right, there's nothing left. So what that's telling us is, actually, it's very likely the dwarf galaxies had to be disk-like when they started out in order to retain their gas. And I showed these calculations in particular because, and again, this is the side-on view showing that it's a disk on the left and a spheroid on the right. The reason for showing this is it emphasizes that we're really at the point now where we have to be using supercomputers. So in the earlier modeling that I talked about by Ural, where we looked at disequilibrium modeling, and so looking at dwarf galaxies being torn apart by the Milky Way, we had to do 19,000 simulations in order to study that problem, and so that required a supercomputer. And here we're looking at gas, and again, these calculations are very expensive. So in the final part of the talk, I'm going to talk about the Dirac high performance computing facility and supercomputing in general, and where we're going with that, because that's it's been underpinning many of the calculations that I've shown you in the talk so far. So direct simulation and modeling is vital now to many areas of scientific research. So you'll be aware pretty much of any scientific area that you think of. It's often driven now by, on the theoretical side, it's driven by computer simulations. And the requirements of those models in terms of how much computer time is needed are always increasing, because we want to either, there's several reasons for this. You might want to do higher resolution ones, not just because it makes the movies that you produce look better, but because you really want to understand what's going on at very fine detail. Also, you want to introduce new physics. So you may want to introduce another process, like in the simulation I showed by Claire Cashmore. You don't just want to have the gas sitting there, you want to have stars exploding. So that's an example where you've added in a new piece of physics, a new process that you then need more resolution to understand. We're often trying to couple models because we're looking at things which are on different scales. This applies not just in astrophysics, but in many areas. So, for example, if you're simulating a jet engine, you're going to need to study both the interaction of gas with the sides of the jet and things that are happening on the scale of those atoms, alongside understanding the scale of the whole engine itself. And fourth area, which is of growing importance, is to actually quantify the modelling uncertainty. Up until recently, many simulations were done just as one-offs. You could only afford to do one of them, and then you don't really know what would have happened if you had started out with slightly different initial conditions. So a lot of work is going on to quantify that uncertainty, because that tells you how reliable the simulations are and how much you can trust the outcomes. There's also now in many areas, so we're constantly improving what we can do, and therefore what we want to do with computers. But there's also now a growing requirement that we be able to do these models and simulations at the same time as we're taking observations or doing experiments, so that we can essentially change if we're looking at an object and we can build a model of it and then say, well, actually, if we looked at it in this way or we did this other experiment, it would give us a new piece of information. So again, that is something that you need to be able to do the computing very quickly in that case. So it's not just enough to have a big computer that can do the simulation in a month. You want a computer that's even bigger, so it can do the simulation in maybe an hour. So the Dirac high performance computing facility was established in 2009, and we've currently got, so we're the provider of high performance computing for the theory community in STFC, the Science and Technology Facilities Council. So that covers astrophysics, particle physics, cosmology and nuclear physics. And we've got 4 supercomputers, the memory intensive at Durham, extreme scaling in Edinburgh, the data intensive in Leicester, and the data intensive in Cambridge. If anybody's wondering why there's a map of the UK on this, because you all know exactly where it is, that's for the benefit of, there are, I think, some people in the audience who are not from the UK and maybe less familiar with where all these places are. So why do we have 4 systems? Why didn't we just build one big one? Well, this is because we've actually been, within Dirac, we use the scientific method to design the computers as well, because the computers are, as I've said, there are tools for doing science. So they're just like a telescope is the tool that you use to make observations. Computers are the tool you use to do simulations. And as I hope I've shown you, we're trying to do the simulations to learn and interpret the data. And so we go through a 3-stage process to design our systems. We start out by writing down what are the science questions we want to answer. We then get that case peer reviewed and assessed so that we are confident that is a world-leading plan for the next 3 to 5 years. We then go through that science case and say, okay, if you want to do that science, how would you do that? What kind of computers would you need? And then once we get that peer reviewed to confirm that we've made good assumptions in those high-level designs, we then work with industry partners to turn those into actual individual service specifications. So it's a long process. And we go through it regularly to make sure that we're always at the cutting edge. And what it tells us is we need multiple types of computer to deliver the science for STFC. So we've got different types of science workflows. The 3 types are extreme scaling, memory intensive, and data intensive. and they need different types of computer. So on the left, extreme scaling, that's used for particle physics calculations predominantly, and that is, for those of you who know about HPC, that is based on the new NVIDIA A100 graphics cards. And so that's for calculations where one calculation can use the whole computer, and that's our kind of our largest system in terms of raw performance. On the right-hand side, we've got the memory-intensive system. That's designed for cosmological simulations. I'll show you another one in a moment, but it's the kind that I showed earlier. And what that's giving us is large amounts of memory. So in that particular case, the simulations can still use the whole computer, but they need a lot more memory than the simulations for particle physics. So we've got a large volume of memory on the system in Durham. And at Leicester and Cambridge, we have the data intensive service, which has a range of different architectures, a mixture of Intel chips and GPUs and AMD chips. And so between all of these, we're able to deliver a very wide range of workflows. And so what you see here, or what you will see, is a movie. It's a repeat of the original movie that I showed earlier on, but this is one that has a lot more. Oh, sorry. It is one which also shows the evolution of gas and stars. And so this is much more expensive than the previous one. It's still done by the group in Durham, but it was using the simulation, the system at Durham, part of the Dirac memory intensive service. So I won't show the whole movie, but what you're looking at here, as I said, it's the same as the one earlier on, which was only dark matter. And this one, what you see now is the colored parts are gas. And so every so often what you'll see is the gas changes color. So there it's going red, it's heating up. And every so often again, you'll see what looks like a blast wave going out. And so if you keep watching, I'll wait for another one to appear. But of course, when you're watching, none does appear. So every so often a star will explode, or the black hole at the center of the galaxy will produce a burst of radiation, and then you'll see a blast wave going out. But the key thing is you have a galaxy in the middle that's like the Milky Way, but it's surrounded by this halo of gas, as well as the dark matter that we saw earlier. And so now you see, when you zoom out, you've got the gas distribution around these galaxies. So there's a lot more detail in this. This was a much more expensive calculation than the one I showed earlier, and relied again on the power of the supercomputers that we were able to deliver. So the final thing I want to mention is machine learning or artificial intelligence, and just to say that there's a lot of talk about whether supercomputing and machine learning, that are they in competition, are they different communities? And so the point of this slide is just to say no. Artificial intelligence and HPC are actually they're very closely related and becoming more and more closely related. So the type of computer you want to build to do a simulation or to do an AI calculation, they're becoming similar. So the GPUs that we have in Edinburgh for particle physics calculations are very similar to the ones you would use for AI. The other key thing is that we're building now in our simulations, we're actually using artificial intelligence to drive the simulations themselves. And so there's a number of ways. I'll just mention one here, and that is that we're using surrogate models. So where we're trying to put in new physics or new processes into the calculations, rather than using simple approximations, we're now able to, people are starting to use AI-based models, which give you a much better representation of what's going on. So just to show an example of using machine learning in the kind of calculations that I've talked about already, and this is, if you like, the subtitle of this slide is training a computer. So this is the bit where we're now linking again back to the original training your telescope. This is training your computer, where your computer is the telescope. And what we were trying to do was, this was with my student Amory Gratian, we were looking to build lots of models of dwarf galaxies and really understand what their dark matter properties were. Trouble is, the models were really expensive to calculate, and there were huge numbers of parameters that we wanted to study. And so what Amory used was Gaussian process emulations. That's a machine learning technique where instead of calculating every individual theoretical model, you use an emulator where you calculate a set of models. Then you build this emulator, it emulates, essentially it mimics what you see in the models, but is much cheaper to calculate. And so what that meant was it sped up for a 3-dimensional parameter space. It gave a factor of 20 reduction in the number of models. For a 6-dimensional parameter space, such as the one we had earlier with the disequilibrium models, it would have been even larger. So the speed up would be even greater. And so using machine learning makes new calculations possible that are not possible or would not otherwise be possible. So how does all of this fit together with other fields? And this is essentially where I'll end with a word about training of people. So this is some recent work that I led to draft a science case for supercomputing for UK Research and Innovations. That's the body that funds research in the UK. And the point of this slide is just to show that supercomputing underpins basically everything in science at the moment. And so the case that we put together was drawing from all of these areas. So fundamental sciences was representing the things that Dirac covers, but you've got engineering, climate, biology. So all of science now depends on having access to large-scale computers, and this was essentially building a case from a science point of view. The first part of that process that I talked about earlier, the next stage is we turn that into technical designs, which is what we're actively doing at the moment. But it's not enough just to fund. So this is a case for why does the UK need to fund more computing, but it's not just about buying computers. It's also we need to be funding people. So there's a well-established gap in the wider economy. Now I'm talking beyond academia, that there aren't enough people with the skills to exploit high-performance computing and AI, and that has an important impact on the economy. And so a white paper that several of us were involved in 2019 on algorithm, software, and skills highlighted that there's a real need to train a workforce. And so Dirac does puts a lot of emphasis on training of early career researchers so that we get to the point where we can actually help to fill that skills gap. And because even though Dirac itself is currently focused on a particular set of theoretical communities, the people who work within Dirac, the students often go out into industry and other areas. And so I will just mention we have really critical shortages of all of of a list there of the types of people. Our software engineers, the people who work on our codes, the people who manage our systems. There are not enough highly skilled people, and we have a real shortage. So that's something which we're pushing very hard, and in Dirac that's something we've been very keen to support. And just one example which links this in with the work on AI I was talking about is we run a lot of placements, innovation placements, where we embed a student or a postdoctoral researcher into an industry or another sector. So for example, we've done a lot of work with Guy's and St. Thomas Trust. And these placements in Guy's and St. Thomas are really cool because one of the things they've been doing is using techniques, AI techniques that they've built up during their work as astronomers or particle physicists. They're using that to reduce the number of missed appointments or to support the advanced care for elderly patients. And so there's enormous benefit coming out of this. And again, this is showing how AI, which is becoming so important in many, many fields, is an area where we are focusing efforts in terms of training, but it's also somewhere that there are benefits far beyond the scientific remit of Dirac. So my final slide, I hope I've given you a sense of how computing, AI, observations all fit together to try and understand dark matter. So I've given you a sense, hopefully, of my some of the work that I've been doing and the work that now we're doing within DIRAC. I'll just take 1 minute because it's something that in an inaugural lecture, it's one of the few opportunities you have to thank people who you don't otherwise get an opportunity to thank. So this slide summarizes a number of people that I want to thank who've been immensely important in my career. Starting at the top, there's Tony Kelly and Ronnie Wallace. So they were two of my secondary school teachers. I believe Ronnie Wallace is actually in the audience here tonight, who were immensely influential early on in my school and beyond. Everett Muirs and Wyn Evans were my master's and PhD supervisors. Jerry Gilmore and Andrew King were the heads of the research groups that I worked in at Cambridge and at Leicester. And Melvin Davis, Carlos Frank and Graham Wynne were colleagues who gave an enormous amount of support and advice over many, many years. So I'm very grateful to all of them. My students, several of whose work I've discussed in this talk, Damien Quinn, Ur Oral, Peter Haig, Claire Cashmore, Amory Gratian and Rob Sanders. Obviously, all my collaborators on papers, there's far too many to mention, so unfortunately I can't, but thank you all. And my co-authors and obviously the many colleagues and friends I have at Leicester. At DIRAC, it's a very much a team effort. There's a lot of people in the team, and I'm grateful for their support since I've been director over the past years. I particularly want to thank Jeremy Yates. He was the first director, the founding director of DIRAC, and in terms of support and mentorship and friendship over many years, over a decade now. I'm very grateful for that and all the encouragement he's given me. Claire Jenner, who's my deputy director and friend, and I've lost track of how many funding proposals we've written together. We're actually in the middle of writing another one, which is due on Thursday, so we'll be going back to that after this lecture. But it's no exaggeration to say that Claire has been absolutely central to the success of DIRAC over the years that she's been working with us. Lisa Brandt, my PA, keeps everything running smoothly and keeps track of where I'm supposed to be and when. Very grateful to her. And then outside academia, there's mum and dad, Brian and Heather, who are on this. I think everybody in terms of family are here at the moment. There's my brother Ian, his wife Andrea, my niece Lucy, my nephew Matthew. Thank you to all of you for your support over the years. And finally, to my partner Sekula, and our daughter Shanti, and our 3-year-old or almost 3-year-old son Kai, who I think is probably going to be knocking on the door very shortly. And so with that, I would like to thank you all for your coming to this talk tonight. I hope you found it informative, and I'll now hand back to Sarah Davis. Thank you.
Thank you, Mark, for that really fantastic lecture. I thoroughly enjoyed it. And I think back in around about 1996, I was giving a geology public lecture, and one of the questions at the end was, isn't it just all about the dark matter? And I think today you've shown that it is all about the dark matter. And I think some of the things that you've talked about as well, about the importance of the data and the people. You started off with that at the very beginning about the discovery of dark matter, and you brought it round at the end, both in terms of the people we need in the future, but also the importance of our colleagues and our families to deliver this groundbreaking science. So I'd just like to thank you so much, and I'd like to thank the audience online as well for attending this wonderful inaugural. Good evening, and thank you.